Hello students, myself Kishore N. Gujjar, Assistant Professor. Today I am going to deliver a lecture on waves. There are two methods from which we can transfer energy from one point to another point. First one, the particle motion. In particle motion, particle itself carries energy from one point to another point. For example, when we throw a stone on a glass, we know that the glass brokens because the stone transfers energy to the glass. If you assume the stone is a particle, the particle carries energy from one point to another point. Second one is the wave motion. In the wave motion, it's a wave carries energy from one point to another point. Then we have to know what are waves. Wave is nothing but a physical disturbance that propagates through space and time. For example, when we drop a stone on a white pond, it produces a water wave. That means the physical disturbance, it produces waves. Next, we'll move on to types of waves. There are two types of waves, mechanical waves and non-mechanical waves. Mechanical waves are those waves which requires material medium for their propagation. And in mechanical waves, the energy transfer takes place from particle to particle, which means when the disturbance is created at this point, this particle is start to vibrating about their mean position, and then that particle is transferred to the energy to the next particle. Then the next particle is start to vibrating about their mean position, and this particle is transfer energy to the next particle. Then this particle is start to vibrating about their mean position. In this way, here the energy is transferred from one point to another point. Example, sound waves and the seismic waves. Next one is non-mechanical waves. The wave which do not require any material medium for their propagation, that is here what we call non-mechanical waves. All electromagnetic waves are non-mechanical waves. Mechanical waves are further classified into two types, transverse waves and longitudinal waves. The transverse waves are mechanical waves where the particle of the medium vibrate about their mean position perpendicular to the direction of the propagation of waves. Here, this particle is start to, suppose if you assume this is the direction of propagation of wave and this is the particle vibrate perpendicular to the direction of the propagation of wave, then such waves are called a transverse waves. The longitudinal waves are mechanical waves where the medium vibrate parallel to the direction of waves. Such a wave, it consists of several compression and rarefaction. The rarefaction is the farthest distance apart in the longitudinal wave, and compression is the closest distance together. Or simply we can say that in the transverse wave, the particle vibrate perpendicular to the direction of propagation of waves. So in longitudinal waves, particle is vibrate along the direction of the propagation of waves. So here the particle it undergoes back and forth motion in longitudinal waves. Next, we will move on to a progressive wave. A wave which moves continuously in a medium without changes its amplitude, then such waves are called a progressive waves. Next, we'll move on to the characteristics of the progressive waves. So, first one is the disturbance produced at a point in the medium is propagated due to elasticity and inertia of the medium. Since it is a mechanical wave, it requires a material medium. So that material medium, it possesses the property of elasticity and inertia to travel the wave from one point to another point. So there is a transfer of energy without transferring the medium. It means that suppose if we assume the disturbance is created at this point, then the particle at this point is start to vibrating about their mean position. Then that particle transfer energy to the next particle. Then that particle is start to vibrating about their mean position, and this particle is transfer energy to the next particle. Then this particle is start to vibrating about their mean position. In this way, energy is transferred from one point to another point without transferring the medium. Third one is the no particle is at permanent rest. Every particle vibrate about its mean position with the same amplitude and with the same frequency. I am already told that when the disturbance is created at this point, the particle start to vibrating about their mean position and it transfer energy to the next particle. That particle start to vibrating about their mean position. So here there is no transfer of medium. There is only a transfer of energy from particle to particle. So that's why here the no particle is permanent rest. At a given instant, phase of different particles are different. There is continuous and regular phase difference from particle to particle. The phase of one particle is transferred to the next particle with a definite velocity called phase velocity or wave velocity, which means that when the particle start to vibrating about their mean position, it transfers the energy to the next particle. If you assume the two particles, one is at this point and another is at this point, or one is at this point and another one is at this point. So the phase difference between these two particles is about 90 degrees. So that's why there is a continuous and regular phase difference from particle to particle. Then the wave velocity is different from the particle velocity. So here wave velocity means velocity with which the wave propagates, and particle velocity is the velocity of the particle about their mean position. So that's why the wave velocity is different from the particle velocities. The wave undergoes a reflection, interference, and diffraction. So next we'll move on to general equation of one-dimensional wave. Now let us consider the progressive wave traveling along a positive x direction. At any instant, the displacement of the particle is given by y is equal to a sin omega t. So here a is the amplitude, omega t is the phase, omega is the angular velocity or angular frequency. Now let us consider another particle P, which is at a distance x from O. We know that for path difference lambda, the phase difference is 2 pi. So for path difference x, that is between the two particles, the phase difference will be 2 pi by lambda into x. That is because we know the relation between path difference and phase difference. So the relation is given by phase difference is equal to 2 pi by lambda into path difference. So thus at a time t, the phase of the second particle is become omega t minus 2 pi by lambda into x. So the displacement of the second particle is given by y is equal to a sine omega t minus 2 pi by lambda into x. So here now if you put omega is equal to 2 pi by t, that is because we know that omega is equal to 2 pi f and f is equal to 1 by t. So that's why omega is equal to 2 pi by t. And this equation become y is equal to a sine 2 pi by t minus 2 pi by lambda into x. Now if you take 2 pi as common, then this equation become y is equal to a sine 2 pi into t by t minus x by lambda. If you put 2 pi by t is equal to omega and 2 pi by lambda is equal to k, that is nothing but propagation constant, then the equation become y is equal to a sine omega t minus kx. We know that the relation between the velocity of the wave is given by v is equal to f lambda and f is equal to 1 by t, then the lambda is equal to vt. If we substitute the value of lambda is equal to vt, then the expression become y is equal to a sine 2 pi. Here this is vt by lambda minus x by lambda. So if we take the lambda common, then y is equal to a sine 2 pi by lambda into vt minus x, or y is equal to a sine omega t minus kx. So these are the different form of the progressive wave that travel along a positive x direction. Thank you.